And the first, number 2, we looked at it here, and there is a simple proof to this fact that if you just look at the Euler criterion and how this Legendre symbol is defined, there's a simple proof to the fact that when this one is necessary and sufficient condition, where -1 is a square, but we took a hard approach, right? So let me summarize it. What we did over there is the following. If this is one, if and only if, that we call that square root of -1 zeta, but you can use I, if that's familiar to you, then what was the relationship between these two fields? The bottom field plus a potentially bigger field extension here. If this is a square, -1 is a square mod p, then adjoining doesn't make any difference, right? So that was no proof. That's pretty much the definition of this thing being 1. You agree? But we started from here and then stated some silly statement. Fp has now order element of order 4. So another thing is that order of this element is a 4. That's another thing we noticed, right? Zeta. Now, I'm not writing down the p anymore because we are in the field. You know, going over a field, it doesn't change anything. So I omitted the p, subscript the p in there. So this one has, Fp now has an element of order 4, right? So I'm keeping this one direction arrow because it's obvious. Here is an order 4 element right there, and it says it's inside there, right? So this is pretty much an easy one. But the other direction, we took a little bit of time, and there we actually use, especially counting lemma, right? Remember the counting lemma? If you have 5, and there's at most 5 elements of order dividing 5, or whatever that number is, right? Because of that, if you have different description of number, they all have to fit in to that tiny set. So they're equal to each other. So behind this one, there was a counting lemma. We're going to summarize it again. So what's that? And after that, order, you know, the size of this multiplicative group, a multiplicative part is Fp star is p minus 1, right? So if we have an element of order 4, that means a 4 must divide, divides p minus 1. Where did p minus 1 come from? Right, it's the order of a primitive roots and size of Fp star, right? That should, or you can look at it as a Fermat's theorem. You know, all the order must divide this p minus 1 because this is true for all elements, non-zero elements in Fp, right? So that eventually gives you p is congruent to 1 mod 4. And that was homework, right? So putting all this thing together was a homework problem, right? Yeah. So let me summarize it like this, and I wrote it here as a big picture that we're going to follow when we go to the p, when you go 2, when you go to 3, and then we're going to go to 7, and all that thing kind of follow this structure. So let me summarize it here. So I call that it's a big picture. We started with the square root of -1, right? This is in question. Is this exotic or still inside Fp? That was the question. The next thing I consider here is that nice description of, it's a nice description. That's one way to, couldn't find any better word. Nice description of this one, which was order 4 elements. This is, I think, it's the first time I'm using a zeta with the subscript 4. I'm indicating that it's an element of order 4, right? Even if you go to the, you know, a lot bigger field extension, you don't get more elements of order 4, right? We kind of stuck to the elements of order 4 we have. What is that lemma? Counting lemma, right? Doesn't matter how big field you look at, is always less than that number. So order 4 element we happen to have here with nice description. This is order 4 elements, right? Yeah. If we change this top number, we don't have this given element as order something anymore, independent of p. So this has nothing to do with p, right? Square root of -1 having order 4 is independent of p. So I think that's one thing I'm going to throw out in here, emphasize That's right. It's independent of P. That is bottom number in the P in there. And next thing we do is that, all right, this is going to be, this one having order of 4 has nothing to do with what the P is. Now the next goal is putting this one, kind of pushing this one down to FP. If this one is inside or not, right? So I'm going to use this term, pushing this one down. This relationship here is a formal, pure algebraic relationship. It has nothing to do with P, right? Next thing we do is that this one is potentially above, potentially this one is bigger, and we try to push this one down here, right? So that this one holds. So potentially this is a bigger field. What condition on P will guarantee that this one, this element that we're looking at is actually lives down there? So what I wrote in here is a pushing down. Pushing this root -1 down to what field? FP. That's the very bottom field. Potentially was up there. So our goal is that we want to push it down. And how can that happen? And that all what this one says here in these two parts is that definitely creates some sort of condition on P, right? Condition on P and mod, in this case, 4 in here. That the part that we have an order 4 element. So how is this order 4 fits into that FP mod, you know, this world where everything is raised to P minus first power becoming 1. And that kind of gives you modulo relationship of P mod 4. Okay, that's a big picture, and that's roughly the theme. We look at some square root of something. We don't know if it is inside the FP or not. And we create a nice relationship that is independent of P. It has nothing to do purely algebraic. Therefore, if it is really complex numbers, whatever, that pure algebraic relationship is always true, no matter which world you live in. That's the thing that we're going to look at. And then you think about how going to, you know, under what condition can we push this square root down to that smaller field FP. And in that process, you will see P must satisfy some sort of congruence modulo of the order element there, right? This is the big picture that mathematicians kind of went for and realized that this can be done. A lot nicer and elegant than what Gauss did. Of course, Gauss discovered this whole thing back then, but in a very, very explicit way, and that's what we're going to see. But if you kind of focus on this picture, the calculation we do and all that, the thing is kind of, hopefully that makes more sense. I'll try to put things into this kind of framework. All right? Okay. So that's the one thing that I want to clarify. So we're heading to case 2. It's number 3, 2 of P. And when is this a square, right? First, let me make a comparison with what we just did. Over there, we started with the square root of -1, right? Square root of -1, that was the earlier case in inheritance. And I call that one zeta, right? And then what was the interesting property of this one? Zeta to the 4th is 1. So you already know the order has nothing to do with the P. But if you start with the square root of t, square root of 2, if you call that one zeta, the order varies. You can just try P, different P's, right? So we don't have that statement. So Gauss' approach is slightly different. And from here, right? So the square root of 2 is our target. So this is the big picture that I was trying to summarize it here. Here's a nice description of square root of 2. Nice description. Square root of 2. He comes up with a nice description with what do we do? Oh, with order of element 8, whether it's down there or not. Right? I'm going to explain where that order comes from. Let's motivate later. So square root of 2 is not order 8. But if you imagine an element of order 8, if I have FP, does that always have an element of order 8? FP, an arbitrary FP. You can't say that, right? Think about P equals 5. Does that have an element of order 8? It only has 4 elements, right? So it doesn't have an order. So it could be an imaginary number. But once you have an element of order 8, you can describe square root 2 very nicely. Independent of what? P. It is not this pure algebraic relations. You go to a complex number world, and you can write down square root 2 with the primitive root, 8th root of unity. That's this pure algebraic relation. So actually, that's just what Gauss was doing. He didn't think about the finite field. Finite field is a lot simpler, nicer way to approach it. All right. Next thing, what was the next thing in there? We're pushing it down, right? Pushing down. What are we pushing square root 2 down to what field? FP. That was kind of varying down there. So we try to put that square root 2 using that algebraic relation. So by looking at that algebraic description, how can we push that square root 2 down to the FP? So that hopefully puts this P into a nice condition. And mod, what would that be? Mod what? Under mod what? If you go back in here, the conclusion is P mod 4, right? Where did the 4 come from? 4th root of unity. That's where it comes from. So if you're in the 8th root of unity, that'll put you in the P mod 8 condition. Isn't that what the supplementary condition is? Right? 1 plus minus 1 mod 8 determines whether 2 is a quadratic residue or not, right? So here's this. If you think about this part of the purely algebraic relations, right? So I actually really honestly knew this too, recognized nicely as a complex number, which was 2 equals 1 plus I, 1 minus I. If I is that, what is that complex number? But also is element of order 4, right? So that maybe that's one motivation. People are familiar with this type of thing. So here's a trick. We want square root 2, right? So you manipulate this one and pull out a square. So realize that, hey, 1 plus I, 1 minus I, maybe that's a nice thing to pull out. So they decided to, I'm going to pull out I in there. If I pull out I, and if you pull out I in there, what happens to that part? It has to be negative I, right? So that if you multiply I squared, negative 1, and positive 1. I is pulled out, so it's a positive 1. Is that right? Right. It's 1 minus I is staying there. How about that? I is pulled out, so I is being pulled out, but there's no I, so you have to think about, in terms of I, what to multiply. So what is this? 1 minus I, right? 1 minus I is I. 1 minus I squared. We pulled out a square, right? This is a square, very nice. So then when I put the square root, this will be nice description, 1 minus I, right? But what about I? This is a 4th root of unity. This is not a square. So create an 8th root of unity so that it's a square. So decide, all right, why don't we pull out 8th root of unity? So if you square it, it becomes 4th root of unity. So that becomes I. That's the one motivation of pulling out 8th root. It's very special for 2 cases. For 3 and on, it's a lot more natural than this. Okay? But here's another approach. So let me go ahead and do that. Let me finish it. 2 is now, what is this I? I is the 4th root of unity. So 8th root of unity is there. Then if I just switch back to just zeta without 8 in there, then it's going to be squared. If you look at the order formula, that becomes order 4. Order 8 element raised to 2nd power becomes order 4 elements. Right? So, or you can just decide, I don't have this one. I'm about to put the square roots so that I can create the square root 2, right? But I don't have this element root I. So why don't I define it to be zeta? Then I think about what could be the order of this guy. And then I figure out its order is 8. That's another more natural motivation. If this is not a square, I'm going to make it a square, right? By putting the square root and having this one somewhere in an extension. And I realize it's order 8, right? Good. So that's what zeta is. So zeta squared now is 1 minus, how do you write I now? Have a different expression in terms of zeta. Zeta squared, right? Zeta squared is I, correct? So zeta squared. Any questions so far? Everybody understand the rise of zeta there? 8th root of unity? Forcing the square root of I exists somewhere. Right here, that's more natural here. Forcing it, all right, I don't have square root of I. What is it? Turns out it's an order 8 element. All right, we're familiar with the throwing in order some element, right? So throw in order 8 elements. and try to write down everything in terms of I, now in terms of zeta. So that's what it is, right? Now we can put square roots. Square root of 2 equals square root of there, and 1 minus square root squared, right? Not worrying about the plus minus 1. There's no distinguished notion of plus minus in the finite field, right? In the real number, it's really something. But here, so not worrying about, just saying that this order 8 element zeta times 1 minus zeta squared, if you square that element, it becomes 2. So that must be the one of the square root of 2. They're always a 2 square root of something, right? Plus or minus. But we don't know which one is. For example, if you think about, somebody called it, wake up and I don't like that I. Who would have known which one is I and minus I? So they call it, this is I. I'm going to call that, it's my negative I is another, whose square is negative 1. Negative I squared is negative 1. So I'm going to call that negative I, not the other one. But the point is that there's no way to distinguish this imaginary number with a plus minus 1. Plus minus I, plus I and minus I, if you swap the role, there's no way to distinguish it. Things like that. Here, if you're looking at two elements whose square is something, there's no way to distinguish that term if you're not in real numbers. All right, so we found it, right? All right, so that's one description, but later on, this is nice description, nice entrance to this manipulation. Later on, what we do is that try to, not thinking about how we pulled out this order 8 element, but just thinking about if I have an order 8 element, how am I going to actually create this type of thing? Just a slightly different context. So here's approach 1. So here's a different approach. God-given number 8. Somebody told me that order 8 will do it. So we're about to figure it out. Order 8 is this equation, x to the 8 minus 1 equals 0, right? An element of order 8 satisfies this equation. Okay? But order 2, order 4 also satisfy that, right? So we factor it out to see which is the defining equation. So x minus 1, x plus 1. You see that x squared minus 1? What is the remaining part? Let's not skip this one. X to the 4th. I think this approach is better. X to the 4th plus 1, right? A squared minus b squared? Correct? So what do you think, this part here? Everything that whole order 4 is just shoved into that part. Do you think, right? Everything that has not order 4, what about order 2? Where do they go? I think all the order 2 goes here. Right? All the order 4 goes there, right? And all the order 1. So do you think that x to the 4th plus 1, what kind of elements satisfy this equation? Everything that has order 8, exactly order 8. How many elements are there in order 8? According to order formula. Euler phi of 8. Remember that? Euler phi of 8 is the number of elements of order something. Okay? So what are they? I think it's 4. Right? Euler phi of 8 is 4. 2 to the 3 minus 1. 4. They're all in here, right? So everything that appeared in there. All right. So here's a unique factorization property of a polynomial of a finite field. All the order 4, if I call one of the order 4, don't you think it's going to appear as a factor? Is that right? It's going to appear as a factor, right? What is the other order 4 element look like? X minus, you can't raise the second power. You know, if it's the second power, then it becomes order 4, right? This is not order 5, I was misspeaking here. This is all order 8, right? This is order 8. If you square it, it becomes order 4. It has to be relatively prime exponent to the order, which is 8, right? So that's the third. Think about the order formula. GCD down there should be 1, not touching the original order. What is the next power? 5, right? Next power? Is that 7? Right. So we got all the 4 elements of order 4 should appear as a distinct factors in the polynomial, right? What theorem? Unique factorization property of a polynomial over a finite field. It's not a ghost. Once it appeared, it must be there, right? That's the unique factorization property. Now here's some beauty in here. If you stick in 1 to the left-hand side, what happens? 2. And the right-hand side? Boom, boom, boom. Things are about in terms of zeta. That's the magic. So you plug in 1 in here, it becomes a 2, right? You stick in 1 everywhere. Here's a 1 minus zeta, 1 minus zeta cubed, 1 minus zeta to the 5th, 1 minus zeta to the 7th, right? You can expand that, and expanded version here, I forgot to write down expanded version, so let me write down the expanded version here. Expanded version is, what is it? Zeta minus zeta to the 4th, is that right? Up there, I forgot to expand it. What do you say? Is that correct? Any question so far? All right, so you can expand this one. It's some work to do that, right? And what relationship you use to bring it down to the lower degree of a zeta? Zeta to the 8 is 1. Zeta to the 4 is negative 1, right? That's even better condition. Does that make sense? Think about how you multiply it in your reading testing. Multiply all that out. Zeta to the 8 is going to be 1, and so on. Yeah, did you have a question? Yes. So whenever this is composite, and there's a good chance that it's split like this, it actually already split. And this, with this condition, if you stick it in 1, and then you get into this wonderful formula, right? Cool. So from here, there's no square yet, right? But think about how the square is pulled out, and this is the next trick that's used for all the other infinitely many things. Got to pull out a square. Fantastic observation. Is here 1 minus e to the 1 there, 1 minus e to the 3rd. All right. Maybe there's many different ways to pull out a square, but what if I can, change the expression of this one and kind of pull it over here, and redundant thing is happening. So, what other expressions do we have other than z to the 5th? There's a mod 8 world in the exponent. We've been drawing this commutative diagram 50 times to get used to it, right? But at this point, now separating the entire thing from the exponent, is that kind of familiar now, if you feel comfortable? What's happening up there in the exponent level is a mod what world in here? Exponent world is, what kind of world is that? Z mod 8. Order 8 is happening in the mod exponent world, right? So when you look at those exponents, you can freely replace it with modulo 8 expressions, right? So what other nice expression do we have for 5? Negative 3? Negative 3 is the trick they pulled out, negative 3. Do you see some overlap? Z to the 3 is there, and z to negative 3 is there, right? Maybe that's going to give you what? Square expression, right? So that's, this is an amazing observation they pulled out. What about z to the 7th? Z to the negative 1. Wow, that's nice. There's a square. It's already just like those cards shuffled over each other. So there's a 2 over. So let's just go for, what should I do to pull out z to the 3rd? Is that I kind of realize I have to pull out this thing, just like I pulled out I. It's a lot easier now because so the trick is that you have to pull out negative as well so that it really looks nice. All right? So I want you to focus on this part. This is not so fast. Let's just do this natural. It's natural to pull out this negative 3rd power, right? Correct? All right. Then what happened to the first one? This one's negative 1. I'm going to pull out z to the negative 1, and that's negative 1. That factor was exactly pulled out. But what about this space here? It was 1 before, so what should be the power? It was 1. It's z to the 0, right? Shouldn't that be to the 3rd power? Such that when you expand it out, 3 and negative 3 becomes 0, and z to the 1st. Z to the 0 is 1. Is that right? All right. So what about this one here? Z to the 1st. We pulled it out. So do you see kind of is happening here? They're exactly the same except the 1 negative sign. So let's see. Here's how many negative ones are here pulled out? It's exactly 2, right? What was this? Number of things that is kind of divided by half in here, right? Over here and everything is shuffled. All right, so 1 minus zeta squared, is that right? And 1 minus zeta cubed squared, is that right? Yeah. So we got the square. Negative 1 squared is that, so we have 1 minus zeta, 1 minus zeta cubed squared. Because the order 8 very special in this case, and this further simplifies to what we had before. Okay? So that's one method. But we're going to stick to this version in here. This version. Simple enough. But I'm claiming that if you looked at the inside, expand out and further, and you'll be able to simplify down to zeta minus zeta cubed. All right? So that's what I mean by square root 2, a nice description with the 8th root of unity, or elements of order 8. That's nice description. All right? Next bit is this, what is the big picture? Now we have this one. We're thinking about this action in here. We want to push down that square root of 2 down to fp, so that we got this condition p mod a, right? And that was very nice and easy and natural when you look at root negative 1. That was the order just did it, right? But here is different. And here's the new thing that kicks in. But this new technique prevails for all the other cases. All right, so this business here, I was labeling pushing square root 2 down, right? How can we do that? If you understand the meaning of it. What do you mean by this one is under what condition of p modulo 8 we can guarantee that square root 2 is actually pushed down to fp. That's the meaning of this thing. So here is the known as freshman's dream. This is an official term. I didn't make up this one, right? Freshman's dream. X plus y is an element in the field extension, such as x comma y is not in fp. This is the key part. It is not in fp. It is in a field extension, f, the bigger one, all right? If you raise the p, and this is what you tell your students that you should never do that, right? But it's okay now, as long as it's an extension of fp, right? Actually, you did that with a 9th power. That was a homework exercise. It asked you to actually raise this one to the 9th power, and then you did this like 5-6 line calculation. You realize that everything in between became 0. You only got x to the 9 and y to the 9. Do you remember that homework problem? Yes. What happened in the middle there? It always has a factor p in the binomial coefficient, right? But what's p in this world, fp world? 0, right? If you look at the binomial expansion of this one, because p is a prime number, that occurrence of that binomial, the p in that all the in between makes everything 0, and making this leaving this x to the p plus y to the p. If x is really coming from the smallest field, the finite field down there, we even know what happens to x to the p, right? What happened to x to the p? X. What theorem? Fermat's theorem, right? So it's even simpler as x plus p, but if it is bigger, then it is no longer xp. Just raising it to power p is kind of distinguished. This is like tornado swirling up in the bigger field, and down there in fp is untouched. This x to the p, right? Nothing happens to the x. X to the p is x if down there in a finite field. So, and this is like behaving just like the multiplication. So it behaves nicely multiplicatively and nicely additively as well in here, right? And whenever this type of thing happens to action you do, it's called field automorphism. So this is the undergraduate label of this theorem, and graduate label of the theorem is called Frobenius automorphism. So this action is moving everything that lives above fp world, but never touches it. Just like eye of the storm. In fp, nothing happens. Everything else is permuted around, right? This is This is Galois theory. But anyway, without the Galois theory, it should be called freshman's dream. And this is, so meaning of this one is that, think about it, all these things we have it here, think about the main theorem. All the expressions is powers of zeta, right? Powers of zeta. So you have to think of it, this one as a zeta to the something, and then you're raising it to the pth power. And this is a world where reciprocity happens. So this is a reciprocity. The word reciprocity is, of course, a flippant. That's suggestion, right? But also in mathematics, reciprocity kicks in. The role is reversed. And here is when it has happened. What is this world up there in the exponent world? Is a mod what world? Mod 8 world for us, right? Could be mod B. Now we're putting P to the mod 8 world by doing that, right? So this is the action where put this base P that never happens, put it up there to the exponent world where it's a mod 8. If this is mod Q, that's where the world is reversed. We looked at the square root of Q. Is a Q, square mod P or not? That relationship flipped it as a P is a square root of Q or not. That is happening right here by raising this whole thing to the pth power. This is reciprocity action is happening right here. It's a very simple thing, easy to understand, but its role in this theory is significant. This is where that flipping thing is happening. Okay? So now, what? Let's go back to now nice description. Where's nice description? Remember nice description? What was that? Square root 2, right? Is now written as what? Zeta minus zeta to the third. Do you remember what zeta was? Some imaginary number with sole property of order 8. That was it, right? That's the only thing we know about the zeta. Then you can pull out root 2 is generated in this fashion, right? Now, pushing it down, how can we create a condition P mod 8, right? That's our goal. How can we put P into mod 8 world? What was the action? Reciprocity action? Frobenius automorphism? Freshman's dream, right? So you do that. What do we do? To raise the pth power, right? Is that what we do? Yeah. But eventually that's what we're going to do. But raising to some power is what we're going to do. But by looking at this root 2 and thinking about the very first item of our classroom lecture, what was that? Euler criterion, right? Euler criterion. So we're looking at square root 2 down there. Is 2 quadratic residue or not, right? If you raise to p minus 1 power, something will happen. So that's the motivation. But we still have p there. And other number minus 1 is relatively small, so you can give a special treatment. We can still play with that freshman's dream. So think about the main motivation. I'm raising this both sides by p minus 1, not p. All right? What was the motivation to raising both sides p minus 1? To pull out Euler criterion, right? Pull out Euler criterion. So what is that? Euler criterion. Euler criterion has 2 in the denominator, right? But it doesn't have 2 in the denominator. But do you see 2 in the denominator is hidden somewhere? Root 2, right? With the root 2. So you can do it this way. If you feel uncomfortable with bringing in 1/2 in the exponent world, maybe you can split it like this. This is okay. This makes perfect sense. P minus 1 is an even number, right? You can split it like this. Then what happens with the square and the root 2? It becomes a 2, right? All right? And then we're not going to touch the left-hand side, but the pth power is pretty nice, right? So I'm going to write it like this. It's zeta q pth power. We pulled out. Freshman's dream is going to happen. C minus zeta to the third. Is that all right? Negative 1 goes to the denominator. Now, what happens to the left-hand side? Left-hand side, simplified version. Boom. What is this? Legendre symbol. Don't you think? Euler criterion. This tells you whether 2 is a square or not, right? That's the condition. We want to push it. This is a pushing it down. Pushing down, right? Pushing down what? Square root 2. We want to push it down. And what condition allows you to do that is right-hand side. Right-hand side. What happened in the right-hand side? P was put into what world? Mod 8 world, right? So freshman stream. Zeta minus the cubed. Zeta to the pth minus zeta to the 3 pth. Right? Now, P is arbitrary, not arbitrary anymore. It's either 1 mod 8, 3 mod 8, 5 mod 8, 7 mod 8, if it's an odd prime, right? Although P is an arbitrary, now is an P mod 8 is what is governing the right-hand side of the situation. So all that you have to consider is 1 mod 8, 3 mod 8, and so on. Okay? So, why don't you go ahead and consider these 4 cases. In front, these two ladies. Sorry about that. Consider 1 mod 8 and 3 mod 8. Back there, 3 people. Individually, consider 5 mod 8 and 7 mod 8. So namely, think about this one. P is up there, but it is completely governed by this modulo 8, right? So replace it with 3 mod 8 case, 5 mod 8 case. That's what's going to determine this value. Does that make sense? Right. Z to the 16 is not really z to the 16. This is the same as z to the 16. 16 is a 0 mod 8. That's what's happening. Let's try one more number, like, for example, 6 here. Let's say, what is it? 10, right? Z mod 10 looks like complicated, but all the modulo 8, z to the 8 is z to the 0. So you can reduce to what number? Z mod 2, mod 8, right? Because z mod 8 is z mod 0. I mean, z to this 8th power is a z to the 0. Zeta to the 0. Does that make sense? What happened in exponents can be replaced in modulo 8. Freedom, whatever you can do. That's the second column of the vertical map of commutative diagram. That's exactly what this is. All right? So go ahead and replace the P with 4 possibility. If it's a prime, it must be odd residue. Was a tricky calculation, wasn't it? So let's look at the second line. So 3 and 9 agree? It's easy, 3 and 9, right? So 3 stays there, 9 reduces to 1 mod 8, right? So 1 there is just an opposite sign. So that was easy. So if you replace this one in the right-hand side, what happened to the right-hand side? -1, right? Right-hand side is over here. Okay? So the 5 is tricky. And how are you going to do this one consistently when these numbers get bigger is really interesting part. Right now, as a small, you can just juggle around and figure it out, right? So here is a 5 and 15, right? 5 and 15. Forget about this part. Was unnecessary, inefficient thinking. 5 and 15, I reduced to 5 and 7. I realize that's better, right? The goal is that you know, because if this is true, no matter what, left-hand side is at 1 and -1. That's the only possibility. So you have a confidence that you can pull out zeta minus zeta to the cube, right? So look at it here. How am I going to pull out first power and third power? So this is the lowest power, zeta to the 5th. So if I pull out 4th power, that leaves what first power, right? So that's the motivation of pulling out only the 4th power, because I want to have this one in there. So pull it out in the zeta minus zeta to the cube. Fortunately, that's going to cancel. Think about zeta to the 4th. What is zeta to the 4th? Zeta is an element of order 8. Zeta to the 4th must be -1. So the next time if you raise to second power, it becomes 1. It has to be -1. So that one becomes -1 like that. So cancel. What is that right-hand side? Remains -1, right? And 7 was a 7 and 21. 7 stays at 21, reduces to 5, mod 8. In similar number, so I pull out z to the 4th again. Then you have this order, but that's -1. That puts this one in the right order. It goes to the denominator, and right-hand side becomes 1. Right? So 1, -1, -1, 1 is the O possibility. They're completely classified by the modulo mod 8 property of P. Right? That's the last business. Because of this fantastic equation right here, and P appearing there nicely like this, forgetting about the binomial expansion. What is that called? Freshman stream, Frobenius automorphism, reciprocity action that's happening that allows you to put this P under mod 8. Originally, 2 was under mod P, right? And that reciprocity happened right there. So who wants to go for final statement in here? What were we doing here? And here's left-hand side. I want you to look at the left-hand side and come up with some guy's name starts with L. What is it? Legendre symbol. What is that Legendre symbol there, left-hand side? Is it 2P? Is that right? This is mod P world. Anyway, the entire thing is happening in the mod P world. Only the exponent is mod 8 world, right? So left-hand side is that, and right-hand side is what? This guy varies, right? This is going to be 1 when, what condition? 1 and 7, is that right? So 1 and 7, 1 or 7 mod 8. What is? P is congruent to 1 or 7, right? Then both 1. What about negative 1? When P is not 1 or 7. The other cases, right? 5 and 3. 3 and 5. What have we done here? We took care of the second supplementary law. Y is a 2 quadratic regional. Again, there's a simpler proof than this, but it puts you in this situation if you're dealing with this field extension so that you understand number 1 of the law of quadratic reciprocity better. All right? So let's review. What I wanted to review here, and going back to that big picture. Remember the big picture? So let's just get familiar with this thing. We start with the square root of P in mod what world? Mod P world, right? So we want to see 2 is a square root of mod P or not. And we actually went to bigger world. For some reason, we looked at 8th root of unity. And because there's nice description of 8th order of elements of order 8 in terms of square root of 2. In finite field is weird. Once you have this order 8 element, you can write down square root of anything. Square root of 6, whatever. There is a description. So every square root is described in that small extension. But this comes from rather pure algebraic sense. So this statement is global. It works in complex numbers as well. That's what I mean by nice description. So with that, our goal was of pushing square root down to FP, right? Our goal is that we want to have the square root down there in FP, right? And that will probably cause some condition P mod 8 that was very vague back then. And we're just guessing that what happened with the order 4 element square root negative 1. Now, what is this thing? Which theorem is doing this action, making available to allow to think the P mod 8? What was that? That was freshman stream, right? Freshman stream is allowing you to put that P in the mod 8 world. This is where the reciprocity action happened. P was the base field, and now all of a sudden P is the target mod 8. So that's what happened. Make sense? All right. So we're going to do 7, right? Let's do 7. What did we just do? We just did 2, right? And 2 was very special. Mod 8, that was. But here, from now on, this is natural. 7, or square root of 7, right? Mod where? Mod P, right? Mod P. And I think we only have a time to cover going to the next spot. Nice description. That's the time we have. So nice description. Nice description of what number? Square root of 7. It turns out it's not square root of 7. It actually turns out a negative square root of 7. Sorry about that. And from there, you do have an expression of the square root of 7 that depends on a little bit of thing. So it's not global. It's not working for complex numbers as well. But negative square root of 7, square root of negative 7 works. In terms of zeta, which is 7th root of unity. Not the 7th root of unity. All the elements of order 7, that's what I meant. If you have an element of order 7, you can describe root negative 7 nicely. All right? We approach this method here. Let's try it. How does it go? The defining equation. We know about this 7 and its defining equation. So roots zeta. Zeta is this defining equation. Who remembers that one? The theorem that has, p to the q minus 1 elements and all that, right? So what is the defining element? Z to the some power, go all the way down to z to the plus 1 equals 0. Zeta satisfied this equation. What was the highest power? Q to the minus 1, right? Q minus 1. So that was 6th, 5th, 3rd. There, n squared, n plus 1, plus 1. Then unique expressions is uniquely described up to 5th power, right? Because 6th power has this different expression. So you can replace the 6th power with the 5th power. So in the description of elements, you can go up to the 5th power. So the defining equation is this. Then we looked at the polynomial, right? Polynomial is x to the 6th plus x to the 5th, all the way down to plus x plus 1. That's not it. Down here. Okay. So who remembers what to do? These factors, right? These factors. So order prime element, maybe you understand why I put that prime in that condition. 7 is a prime number, right? 8 was not a prime number. So something that satisfies this thing, like last time, doesn't mean that it has order 8. It could be order 4. It could be order 2, right? But in the 7 case, there's no way that there's no other case. If it is not 1, it's going to be order 7, right? So how many elements of order 7s are there in this big field? Counting lemma, there's no more than 6 elements, right? 1 has been removed. All the other 6 elements is exactly order 7. There's no other possibility. So if I have order 7 elements, zeta in here, that appears as a linear factor. What is the next one? Zeta squared, right? Because 2 is relatively prime to 7. Order formula, right? Anything relatively prime to order, you put it in there, order doesn't change. Everything is relatively prime to 7. Do you agree? So it's a prime. Did I put everything now? There are 6 elements. They all have order 7. How do you know this? They all have order 7? Anybody? Why this z to the 4th has order 7? Order formula, right? Order formula has in the denominator. What is the denominator in the order formula? Right? This one. Order 7, GCD of the power 4, 7, and you can see this is going to be always 1, no matter what. 1 through 6. They're all order 7, right? What was the next goal? You plug in x equals 1, and what do you get in the left-hand side? 7, right? That's the magic in here. 7, right there. Right? You plug in a 1. A 1 minus zeta. 1 minus zeta squared. 1 minus z to the 3rd. 1 minus z to the 4th. 1 minus z to the 5th. 1 minus z to the 6th. Right? What do you say? Looks good? Then what is that? We have to pull out square, right? We have to pull out square. What is the exponent world here? The exponent world is what kind of world? Z mod 6? No. Z mod 7. There's an order 7, right? If you reach 7 in the exponent, it becomes 0. So the Z mod 7 is the world. This is the exponent world. All right? So all that thing in the exponent here can be replaced with whatever that works in mod 7. So we did half of the thing and then put it on top of the first half of the thing, right? So we pull out a square. So let's work on this part in here. Who wants to work on this one? 1 minus zeta to the an expression rather than 4, the other alternative that has a smaller. Negative 3, right? Negative 3? Does that make sense? Right. Negative 3 is modulo congruent to 4 mod 7. Agree? And this one? Not mod negative 5. What is it? Negative 2. Ah, you got the pattern. You don't have to think about it. You go down now, right? So 1, 2, 3 showed up. And how did I take care of this negative in the exponent? Remember that part? I factored it out, right? I factor out. Now you factor out negative as well. So you know. No, let's not do that. It's just negative 3 factored out. That becomes z to the 3rd minus 1. You see that? I factor out this guy here. And this one's out, so it's 1. But there was a 1 before, so it has to be z to the 3rd. Remember that cancellation before? So what about next one? Z to the negative 2. And z to the 2nd minus 1. And z to the negative 1. What is it? Zeta minus 1, right? So we have exact duplicate copies, right? And then here. But they're in the wrong order, so we pull out negative 1s, right? But this time they're odd number of negative 1s. Do you see an aha moment? Where is this odd number of negative 1 is going to go? Negative 7 on the other side. All right? So here's a 7. Then I have copies of this one. You see that? Did I copy it right? Here is a 1 minus zeta, 1 minus zeta squared, 1 minus zeta to the cube. They all put it on there, right? Therefore, we have to take care of the negative. If you flip the sign, then we put it over there. So how many a negative 1 is pulled out? 3 of them, right? There's 3 of them there. And let's take care of that guy. What is this? Negative 3, negative 2, and negative 1. 6? Negative 6, right? What is negative 6? Just the zeta to the first. Oh, that's nice. But unfortunately, that's not a square, is it? Zeta, right? But it's going to be a square. You can pull out 2 because 2 is relatively prime to 7. But what are you going to do to the negative? Negative 1 here. I'm going to put it on the other side as negative 7. Some square times the zeta, right? Zeta to the first. What is the problem with the zeta to the first? It's not a square, is it? It's a square, but it doesn't look like a square. How did we make the square? If there's no 2, let there be 2. And you figure out the other part. Modulo what? 7. This is mod 7 world. So if you pull out 2, what's it going to be the other part? Multiplicative inverse of 2 mod 7, right? So that it becomes 1. What is that? 4. Wow. 4 times 2 is 1 mod 7. Therefore, I realize zeta as a square, right? So, square map in mod P world is 1-to-1 map, not D-to-1 map. Therefore, everything is obtained as a square. That's another way to look at that thing. So, we figured out the formula, running out of room. So find the last thing, I'm going to write it down. Where's our formula? Square root of negative 7, right? Who wants to go for this one? We got the kind of square version down there. You have to put the square root of everything. What is the zeta part if you put the square root here? Okay. Zeta to the 4th? Agree? Yeah, that one's square root. And the other part that I didn't write down here because I'm running out of room, they're all squares nicely, right? So I can write that down. What is it? 1 minus zeta, 1 minus zeta squared, and 1 minus zeta to the cube, right? And then there it is. I found the square root of negative 7. Gauss didn't stop in here. He actually expanded this one, and looked at it. Oh my God, the coefficients are always a plus minus 1. So can you imagine you expand this one, and you go to stage, and here it is, expanded it, right? And it looked at it, every coefficient is a plus minus 1. And it guessed it, maybe that's the values of the Legendre symbol. And he was right. And then he expanded it and write it down as a, see all the coefficients are actually the value of the Legendre symbol of a simple pattern. So that's the another discovery of Gauss. But from here, you can still finish up the proof of quadratic reciprocity. But that also gives you greater possibility to generalize whatever is available from there. Okay? So we got that, and next bit is a reciprocity action, right? Raise the pth power and see what this pth power is moving these things around. It's a permutation, and in the midst of it, the Legendre symbol kicks out. That's the how this thing works. But we're going to stop it here, and